Today our title is Molar Solutions and Dilutions. So I have in front of me two solutions. Both of these are copper 2 nitrate. Okay, both of these are copper 2 nitrate. And they look very different, but they're both copper 2 nitrate. Okay, so there's solutions, and what does that mean? Okay, so any homogeneous mixture is called a solution. So homogeneous mixtures, are known as solutions. Not the answer to a problem, but a solution. Okay, so this we call an aqueous solution. It's a mixture of two things, and it's homogeneous. What does homogeneous mean? It means that it's the same throughout. So for instance, vanilla ice cream is a homogeneous mixture. Rocky Road ice cream is a heterogeneous mixture because it's not the same throughout. You can't take a spoonful of Rocky Road and have identical stuff as if you take another spoonful of Rocky Road. There are some spoonfuls of Rocky Road that are significantly better than others because they have more stuff. So it's heterogeneous. It's not the same throughout. Vanilla ice cream is homogeneous. No matter where you take your spoonful of ice cream, it's going to be the same. Okay? So we would actually say that vanilla ice cream is a solution as well. So solutions can be solids, liquids, and gases. So it's simply a homogeneous mixture, so more than one thing, and no matter what portion you take of that mixture, it's going to be identical to any other portion. Okay, so these are two homogeneous mixtures, so two solutions. And these are aqueous solutions of copper 2 nitrate, meaning that I have copper 2 nitrate dissolved in water, an aqueous solution. Now, why would one imagine that this beaker is a darker blue than this beaker? Okay, this is not a trick question, people. We say that it's darker because it's got more copper 2 nitrate in it. It's more concentrated. So this is a more concentrated solution of copper 2 nitrate than this one. It has more solute. More moles of copper 2 nitrate are dissolved in here compared to this. How do I know that? Well, because I chose something that's colored, right? So the copper 2 has actually got it reflects blue. So the darker color is telling us that we've got more copper 2 ions in here than we do in here. Okay, so the concentration of copper 2 nitrate in this aqueous solution is greater than the concentration of copper 2 nitrate in this aqueous solution. Okay, so concentration. The concentration of a solution describes the amount of solute, and in this case our solute was copper 2 nitrate. That is our solute. Describes, the concentration of a solution describes the amount of solute dissolved in a solid got the solute, okay, which is what is being dissolved in. Well, we have the solute, which is, let's go the other way around. The solvent is what it's being dissolved in. The solute is what is dissolving. Now, in an aqueous solution, you know, we don't say that oxygen gas dissolves in nitrogen gas, though they are both part of this solution we call air. So in this case, when we're talking about aqueous solution, it's dissolved in. Something else I wanted to say here, and I can't remember. By definition, right, we have more solvent than solute, okay? So, whatever you have more of, you say that's the solvent. Okay, and the other is the solute. Alrighty, now, the greater the amount of solute, the greater the amount of solute, the greater the concentration. The concentration of solute in a solution can be reported in a variety of ways, but we're only going to talk about one way today, and we will talk about more ways later in the school year. So the concentration of solute in a solution is measured using molarity, or is measured in molarity. Okay, we abbreviate molarity with the capital letter M, molar. Okay, so what are our units for molarity? Our units for molarity, so big M, which is molarity, has got units of moles per liter. So the number of moles of, actually, I'm going to put it in a different color, you guys. Moles of solute per liter of solution. Okay, so moles per liter. Moles of solute per liter of solution. So we would say, if we saw something written on a beaker, like 0.5 molar copper 2 nitrate, this is how it would be written, 0.5 molar. And you've seen this. You've seen this in your labs. We've had molarity. You've been introduced to it. You just didn't know it in your lab procedure papers. So what does this mean? 0.5, and this is how we say it, you guys, 0.5 molar copper 2 nitrate. That's the vernacular, 0.5 molar. That means that we have 0.5 moles of copper 2 nitrate per liter of the entire solution. Okay, and we could say it 0.5 molar, just so you don't get confused about the way it's said. So we are looking at a quantity here, sort of like molar mass, in that it has units in the numerator, units in the denominator, and if we're saying that something is 0.5 molar, that number is going with the moles, not with the liters. Are there problems we're going to do? Yes, there's problems we're going to do. So, we've got a couple here. We've got three, actually. Erase this. Let's just stay on the side of the board. Okay, so you guys, I wasn't exact when I made these solutions this morning, but just so you get the point across, let's say this one is more concentrated than this one. So let's just say, just so we've got some frame of reference, it's not true, okay, but we have a frame of reference, that this one is 5 molar. It's more concentrated than this one. Let's just say this one is 1 molar. 5 molar, 5.0 moles per liter compared to 1.0 moles per liter. This one's more concentrated. Okay. So, what does the problem look like? Let's do some. What is the molarity? What is the molarity of a solution prepared by dissolving 11.5 grams of sodium hydroxide in enough water to make 1.5 liters of solution. Okay, now this is a really bizarre question because this really normally isn't the way we're gonna utilize molarity problems. In general, it's going to be the way we'll do the next one. So let's just go at this one, get this one behind us. Okay, so we're looking for molarity, people. We're looking for moles per liter. Okay, so moles per liter is what our units have to look like at the end of this problem. Ooh, we already have liters. But you know what? I don't like to start a problem by 1 divided by the number. So I'm going to leave it for now. And let's go here. Okay, we'll add this in at the very end. So I've got 11.5 grams. And again, you guys, what I'm trying to get to is moles per liter. I already have my liters, so I don't have to worry about it. So really all I've got to do is I've got to be able to convert this gram into moles. So I'm going to start with, I've got 11.5 grams. 11.5 grams of NaOH. Okay, over 1. But grams are not in my molarity units at all. So I've got to get them to moles. And so how am I going to convert grams of sodium hydroxide to moles? I'm going to use the molar mass of sodium hydroxide, which is 40.00 grams of NaOH per mole of NaOH. Okay, my grams cancel. So great, I've got moles of sodium hydroxide, but molarity is moles per liter. So here are my liters. I'm going to put 1 over 1.50 liters. So now you guys, what are my units? I've got this many moles in 1.5 liters. So if we do this math, 11.5 divided by 40 divided by 1.5, what we end up getting is 0.192 molar sodium hydroxide. There's the concentration of the solution. What does that mean? Moles per liter. Molarity. Okay. What else can these look like? Well, when I prepared your lab for finding the stoichiometric ratios, I had to make 0.5 molar solutions of potassium iodide and a 0.5 molar solution of sodium hypochlorite. And so how did I do that? Because that's really the way we utilize this, you guys. And we do it all the time in lab, biology, chemistry labs. All the time you're making molar solutions because you've got to have particular concentrations of things. Okay, so oh, actually, I'm not quite there yet. Okay, let's do another one. How many grams of copper 2 sulfate are contained in 500 mils of a 0.750 molar copper sulfate solution? Okay, there's a mouthful. So let's write this down. How many? Let's do it in a different color pen. How many grams of copper 2 sulfate are contained in 500 mils of a 0.750 molar copper 2 sulfate solution. Okay, so what are we looking for? We're looking for grams. We're looking for grams. So, what am I given? Well, I'm given two things. I'm going to start with this one because this is my 2-unit thing. So, I've got 0.750 moles of CuSO4 per liter of CuSO4. Okay, that's what that means, 0.750 moles per liter. How many liters of it do I have? I have 500 milliliters. 1, 2, 3. So I have 0.500 liters of that solution. Why did I put it in the numerator? So I can cancel it here. Great. Got rid of liters, only got moles, but I'm looking for grams. So how am I going to convert those moles to grams? I'm going to use molar mass. So notice, you guys, we're doing dimensional analysis. We are utilizing dimensional analysis. This isn't a stoichiometry problem, which also utilizes dimensional analysis. We don't have any balanced equations here. We don't have a mole ratio here. Okay, so dimensional analysis, of course, is a tool that we can use in all kinds of contexts. So we would never call this stoichiometry. Okay, we're using dimensional analysis to solve this problem. Okay, so anyway, I'm going from moles to grams, so I'm going to use the molar mass of copper 2 sulfate, which if we were in class, I'd make you calculate it. So we are 159.62 grams of copper 2 sulfate per mole. My moles cancel. Not using grams. And if we do math, you should end up with 59.9 grams of copper 2 sulfate. Okay, we're doing another problem. These are long notes. Describe how to prepare. How to prepare 3.00 liters of 0.200 molar potassium chromate, the solid salt. Okay, so we've got a container of potassium chromate. Chemicals come as solid salts, and we need to make 3 liters of a 0.2 molar potassium chromate solution. The really cool video would be me actually making the solution, and I think I'm going to have to do that for you. Okay, right now though we're just going to write the steps to this. All right, so I want 3 liters of a 0.2 molar solution of this. So what I need to know, really what I'm getting at, you guys, is how many grams of the salt, how many grams of this do I need to add to water and bring it up to 3 liters so that my solution is 0.2 molar? Okay, so how do I do that? How do I figure out how many grams of the salt I need? This is the way we do it. We say, we've got 0.200 moles of K2CrO4 per liter. Okay, this is what we're going to make. And we're going to make 3.00 liters of it. Let me get rid of this. multiply these two things together, that's going to tell me how many moles of K2CrO4 I need. But I'm not going to count out moles. To count out moles, what am I going to do? I'm going to weigh it on a scale, right? I'm going to measure it on a balance. And so I need the molar mass of potassium chromate to convert it from moles to grams, because it's grams that I can measure on a scale. So, where's the molar mass? So the molar mass of potassium chromate is 194.2 grams of K2CrO4 per mole of K2CrO4. And I'm all out of room. There we go, moles, moles. So I've got grams. So now, 0.2 times 3 times 194.2 gives me 116.5, I can't use all those significant figures, 117 grams of K2CrO4 is what I need. And so now how am I going to make this thing? What am I going to do? Well, I am going to add 117 grams of solid K2CrO4 to I'm going to make this easy. A 3-liter volumetric flask fill with water to the mark and mix well. So what that means then, my volumetric flasks, you guys, come in a variety of sizes. I've got this adorable little 50 milliliter, 100 mils, 500 mils, right? Volumetric, it has one line, it only measures one volume. Okay, these things come in all different sizes. 1 liter, 2 liters, 3 liters. So what we're going to do is we are going to measure out on a scale 117 grams. I'm going to have to actually talk about this in the class a little bit. I would measure out 116.5, right? That was my original. That was my original. And these are actually, you guys, all conversion factors. Well, this is a conversion factor. This is exact. 3.00000, 0.20000 molar. And so, in essence, you guys, we have got an infinite number of significant figures that we're working with here. So, I would actually measure out 116.5 grams, exactly what I got when I multiplied it out. Okay, I'm going to measure it out on a scale. I'm going to dump it into a 3-liter volumetric flask, if I have one. And then I'm going to take water and I'm going to fill it up to the mark. And then I'm going to shake it well. And I will have 3 liters of 0.2 molar solution. How else could I do it? I could take salt, I could put it into a big 3-liter graduated cylinder, and then I could fill it up to 3 liters with water. Now, the most important thing, and we're going to do another day of notes tomorrow for this. I'm going to make some solutions and do some dilutions. Is that you don't ever want to fill it up to 3 liters with water and then add the salt. Because what's the salt going to do to overall volume? It's going to raise the overall volume. So it's very important that you put the salt in the container, you add the water, and you mix well, and then, if need be, you add some more water so that it is all the way up to whatever volume it is you're looking for. But I'm going to do that tomorrow. For today, you guys, we're done.